Hello, my name is Kashif Javed and my student ID is CST2509098. In this video, I'll be walking through my C program that implements a doubly linked list. I will be covering the node structure, the 5 core functions, how I handled the edge cases, and also a quick output to show that the code actually works. Before I get directly into the code, here is a quick roadmap of what I'll be covering. First is node structure. This is how each node is defined and why it's called doubly linked. The second thing as written is the 5 core functions: is empty, insert node, find node, delete node, and display list. Thirdly, we're going to look at how the program handles edge cases like an empty list, a single node list, and how to search for a value that does not exist. And finally, I'll walk through a sample run of the program so we can see it working. So let's start with node structure. I defined it using type def struct node, and each node has 3 parts: an integer called data, this one stores the value, and then a pointer called prev, which points to the previous node, and a pointer called next, which points to the next node, the following node. That is what it makes a doubly linked list as opposing to a singly linked list, because every node knows both of its neighbors, both of its directions. I can go through the list forwards or backwards, and I can remove or insert a node using just a pointer to that specific node. I don't need to walk the whole list from the head to find what comes before it. I just need to use a pointer to that specific node. So I also declared a global pointer called head, and I initialized it to null. So head always points to the first node in the list, and the entire list is only reachable through the head. So it gets checked and updated in almost every function. That is where the isEmpty function comes in. It simply returns whether head equals null. So I call this at the start of find node, delete node, and display list. So the program never tries to search or delete from it or print a list that does not have any nodes. So now let's look at insert node. Every new value is inserted at the beginning of the list. And so the most recently added node becomes the new head. So there are 4 steps. Firstly, I used malloc to create a new node and check that the allocation did not fail. Then secondly, I set the new node's data to the value being inserted and set its previous pointer to null, since it's about to become the first node. Thirdly, I point the new node's next to whatever the current head is. And fourthly, if the list wasn't empty, I linked the old head's previous pointer back to the new node, and then updated head to point to the new node. So in the diagram here, inserting 12 puts it at the very front, and the old first node, which was 47, becomes the second node. Find node does a very simple search. I start a temp pointer at head and a position counter at 1. Then I loop. If temp's data matches the value I'm looking for, I print the value and its position and return it immediately. Otherwise, if not, I move temp to temp next and increment the position, and just keep going like that in the loop. And if the loop runs all the way through and temp becomes null without ever matching, that means the value isn't in the list. So therefore, the message will, I print value not found as the message instead. So deletion happens in just 2 steps. The first step is just finding the node. I start with the same isEmpty guard as before, then walk a temp pointer through the list while temp isn't null and temp's data doesn't match the value. If that loop finishes and temp is null, then it means that the value was never found. So I print value not found, cannot delete, and return immediately without touching any pointers. This matters because trying to delete a node that doesn't exist should never crash the program. Once I found the node to delete, our second step relinks the neighbors around it using 3 independent checks. If temp is the head, I move head forward to temp next. If temp is not the last node, I set temp's next node's previous pointer to temp's previous. So the following node skips back over temp. And if temp is not the first node, I set temp's previous node's next pointer to temp's next. So the preceding node skips forward over temp. After all three checks, I call free on temp to release its memory and print a confirmation message. Display list checks is empty first, then starts temp at head and prints doubly linked list, followed by every value in order as temp moves through the list with temp next until it hits null. Free list is only called when the user chooses to exit. It walks through every remaining node, storing head in temp, moving head forward, and freeing temp each time. This releases all the memory I allocated with malloc, so the program doesn't leak memory when it ends. Now for edge cases, which are extremely important, first is an empty list. Because is empty, the function is empty is checked at the top of find node, delete node, and display list. Each one prints a clear message instead of trying to read from a null head. Second, a single node list. If I delete the only node in the list, it satisfies both temp equals head and temps next and previous are both null. So head correctly becomes null again and the list returns to empty with no leftover pointers. Third is in an invalid value. Both find node and delete node fall through their search loops when there's no match, print not found message, and return without changing the list. This is a short run of the program. So I inserted four values 12, 47, 9, and 31. Then display the list to confirm the order. I search for 9 and it correctly reports it's at position 3. Then I delete 47 and displaying the list again shows it's no longer there, with 12, 9, and 31 correctly relinked. This confirms that all the operations of our code, they're working smoothly. Insertion, the display, search, and deletion, everything is working as expected. To sum it all up, each node stores a value plus the previous and next pointers for traversing both ways. So the five functions is empty, insert node, find node, delete node, and display list. These cover the creation, search, removal, and output. So each of these functions prevents against an empty list. And free list cleans up all the memory before the program exits. Thank you for watching, and I will pass on the next question to my team member.
Good evening. My name is Druguna Grace Kabura, and today I will be presenting task 2, which is the implementation of a stack using a singly linked list. So during this presentation, I will explain several things like why a singly linked list is suitable for implementing a stack, how the top of the stack is represented. I'll explain the functions used in the program, how a stack underflow is handled, and finally, I'll demonstrate the program output. So we start by why a single linked list is suitable for implementing a stack. So first of all, a stack follows the last in, first out, or the LIFO principle. So this means that the last element inserted in the stack is the first one to be removed. So a singly linked list is suitable because it uses a dynamic memory allocation, which unlike an array, we do not need to specify the size of the stack before the program starts. And the memory is allocated only when a new node is added and also released when a node is removed. So this makes the implementation so flexible and efficient. So I'll start by how the top of the stack is represented. Yeah. So sorry, the pointer top always points to the first node of the linked list, which is also the top of the stack. So when the stack is empty, the top pointer is equal to null. And whenever a new node is inserted, then the top is updated to point to that node. So when a node is removed, the top is updated to point to the next node. And then I'll go to the add function. So the purpose of this function is to insert a new element at the top of the stack. First, the memory is allocated for a new node using malloc, and then the program checks that the memory allocation is successful, and the value which is entered by the user is then stored inside the new node. Next, the next pointer of the new node is made to point to the current top of the stack. And finally, the top pointer is updated so that the new node becomes the new top, and every new element is therefore added to the beginning of the linked list. And then I'll go to the second one, which is withdraw. So the purpose of this is to remove the element which was currently at the top of the stack. So the function start first checks whether the stack is empty by checking whether the top pointer is equal to null. And if the stack is empty, then the program displays a stack underflow message. So the value stored in the node is saved, and then the top pointer is also then updated to point to the next node. So finally, the memory of the removed node is released using the free function, and the remove value is returned. Next, I'll explain the display function. So the purpose of the display function is to display all the elements currently stored in the stack. So it starts from the top pointer and traverses the linked list one node at a time until it reaches the end. So the elements that are displayed from the top to the bottom, they follow the order in which they will be removed. And then next, I'll go to the counting function. So the purpose of this is to count the number of nodes that are stored in the stack. So the function traverses the linked list from the top to the last node while increasing the counter. And at the end of each of the transversal, it displays the total number of elements in the stack. And then now I'll go to the stack overflow in withdraw. So here we have my program handles this by checking whether the top pointer is equal to null. And if the stack is empty, then the program displays an error message. So instead of like attempting to remove a node. So this also prevents the invalid memory access and ensures the program continues running safely. So then I'll go to the main function. So this is the main function which controls the execution of the whole program. And the program uses a menu-driven interface together with the switch case statement. So the user is presented with four options, either add, withdraw, stack count, and exit. And after the user enters any choice between one of the four, the switch statement calls the corresponding function. And then the menu is placed in a do while loop, so it continues to appear until the user selects exit. So if the user enters like an invalid option, the default like displays an error message. I'll demonstrate the program output. I'll start by the add function, which is the one selection, and then I enter a value like 556. So the 556 becomes the top element since the stack was empty. I can add the next value like 445. So 445 becomes the new top element, and I can finally add another value like 223. So this shows that each new value is inserted at the beginning of the singly linked list. Then now I can perform withdraw, which is selection 2. So 223 was removed because it's currently at the top, and now the new top becomes 445. It also demonstrates the last in first out principle because 223 was the last value added and is the first value removed. Next, I'll do stack count, which is option 3. So this displays the number of elements in that stack. So it shows that there are two elements in the stack, which are 445 and 556. I can then add another value. For example, I add 342. This value becomes the new top of the stack, and the stack now contains 342, 445, and 556. Finally, I can exit, which is option 4. So before the program terminates, any remaining dynamically allocated memory should be released to prevent leaks. So the program has terminated. So in conclusion, this assignment helps you understand how a stack can be implemented using a singly linked list. And among many others, I learned that a stack follows the last in first out principle and that the head of the linked list can also represent the top of the stack. So one challenge I faced was making sure that the pointer was updated correctly after adding or removing a node, and I was able to solve this by tracing the pointer like changes, how it changes carefully, and tracing the program after every operation. So overall, this assignment improved my understanding of pointers, linked list, tags, the dynamic memory allocation, and memory-driven programming in C. Thank you for listening.